Okay. Raza has already introduced, and some of us have already talked a bit about multi-terminal HVDC. So as soon as we have, different wind farms and different grid connections, we will. Well, the logical idea is to interconnect them using an HVDC grid, right? So, well, basically. What I'm going to show you here is a bit how the primary control, the primary voltage control of the grid is being proposed to be done. So there is just one or even two multi-terminal grids working. I think that's one in China, but there's not. It is not something well proven. It's not something well tested. So people keep proposing new ideas, but this is for the primary control. What it's called the troop control, as Raza said, is one of the technologies, is one of the most accepted technologies. Okay, so how does thing work? So as you can see, we have wind farms, offshore wind. We are talking about offshore wind power plants, and then we are interconnecting those offshore wind farms with the main AC grid that can be located far away from the shore, as we have been introducing. Okay, so the main idea is how can we control the voltage there. So Raza has been talking about this droop control. So basically, what we have considered in this idea, what I'm going to explain, is how to regulate this voltage on the DC network. Okay. Let's assume that, for example, the wind farm. Our objective. What's our objective? We want to inject to the main AC grid, where we have the loads, the energy produced by the wind farms, right? So if we have, we are producing 400 megawatts in each wind farm, we want to inject that to consume that in our houses or in industries or whatever. Okay. For that reason, we need to maintain the voltage of the AC grid. Otherwise, if we keep injecting power to the DC multi-terminal grid and we don't control the voltage there, the voltage will go unstable. We have to regulate the voltage there in order to. If we maintain the voltage, inherently we will need to extract from the grid side converters power to the AC grid. So basically what we are assuming here is that we have, for example, two different wind farm converters that are injecting power to the grid, and then our grid side converters are in charge of controlling the DC voltage to extract that power to the main AC grid. Okay, so I have prepared some drawings, like, well, they are a bit weird. They are made by hand to illustrate this idea. Okay, let's see if I can explain it properly. Okay, so assume that you have, for example, let's say n wind farms. That in this case, two different ones. Here you have let's see if this thing works. Here you have two different input powers. Okay, let's assume that they are the same amount of power incoming from the wind farm. Okay, and you have a power step input at both sides at the same time. Okay. Here you can see the grid side connection. If we don't have any control at the grid side connection, if we are not extracting that power, if nobody tells us that we have to extract that power, what could happen? We will keep, maintaining the same power extraction, right? So this is like a water tank. If we are introducing some power there, some energy there, and we are not extracting that water from the tank, it's happening is that the tank is going. I mean, the tank water level is going up. Okay, so this here happens with the voltage. So if we don't extract that power there, what happens is that the voltage start to rise. Okay, and that's something that if we keep this for a few seconds, we will blow up the whole multi-terminal grid, which is not really desirable, of course. So there are different proposals here. One of the proposals is that, for example, Raza explained for the AC hub, but this is for the DC side, for the DC multi-terminal grid. So one proposal is to regulate the voltage from one terminal. So we are using just this red terminal, maintaining the whole voltage there. So if this terminal is in charge of regulating the voltage there, what and it has like let's say a PI controller which is tracking the reference voltage. So if we say, for example, you have to maintain that voltage to 150 kilovolts, it will stuck to that voltage. It won't move. I mean, it will be, for example, a transient, as you can see here. The voltage will do this go up. It will go up and down because it takes some time to balance the voltage, right? To extract that power to the grid. But at some point, it will extract the power. What happens with the other grid side converter? That if we don't implement another PI here, all the power that is coming from this side will be injected from that side. This should be the double of that one, but my drawings are not that good. Okay, so we will regulate all the power that are coming from both those two wind farms will be extracted from this GSC. So somebody can think, okay, what's the next step? So we can include two different PI controllers, right, in the same system, just to control the same, to control the voltage from those PIs, and then we can share the power extracted, right? So what happens if we do that? If we regulate the voltage here, and if we regulate the voltage here, we are controlling the voltage at these two nodes, but the voltage here and here, as the impedances of the grid are not too big, what happens is that there's a interference between both controllers. So it's the same as, imagine that both controllers are regulating exactly the same magnitude. So the fastest one, you have a one that should be faster or lower, depending. You could have different vendors here. One could be the ABB one, another one a Siemens one. You could have, you can imagine that one probably has the voltage loop tuned for 20 milliseconds and the other one for 100 milliseconds or whatever. So you will have some interactions because one will try to, regulate the voltage faster than the other, and the other will see that there's a higher error and will extract more power. So you will see some oscillations like this on the voltage, and this could go even unstable. But what it typically happens is that if you try to simulate this scenario, is that there's a fastest grid side converter which finally handles the whole voltage of the multi-terminal DC grid and ends up extracting the whole power again. But there's some interferences there, and it is something that it is not something that is not desirable. So for this reason, people, manufacturers and people that are working on system operation, on DC multi-terminal system operation, have proposed the Druck control, okay? And what is the Druck control? It's even simpler than a PI controller. It's a proportional controller. So here you can see that it is like this. So you have the voltage measured at the terminals, then you have a reference voltage, which is typically the rated value of or the nominal value of the system. So imagine that you have a plus minus 300 kV system, so you have 640 kV there to regulate. So this should be the reference value, okay? Is the rated value of the system, more or less, okay? Then you have the measurement, so you calculate the error here, and based on that error, you are multiplying that error by a constant k. It's a proportional controller, a classical one, so it's so simple. Okay, so this is basically the main idea between that. And well, for my study, for what I'm going to present here, I assume that there are a lot of stuff going on in the converter, but we have a reference calculation, you have a current loop. I don't know if you have seen how is the controllers of the converter are done, but we were assuming that that these were pretty fast and that you can apply directly the current to the grid. So simplifying the study for this reason. And I'm going to show you again using the same drawings what's going on if we are operating the grid with a Druck controller. Installed one Druck controller here and one Druck controller here. This is the base study again. So it is like the base idea. If we are introducing some power here, if we don't extract power to the grid, again the voltage will go up. Okay. What happens if we include Druck control? If we include Druck control here in the grid side converters, in these two, So here you can see that we have exactly the same thing that I told you. So it's the difference calculation between the reference and the voltage at that node multiplied by a constant K, okay? So if you remember from control theory, do you remember that when you had a proportional controller, there was a steady state error on the system and all the stuff like that, like type 1 controllers, and if you include a PI, you cancel that state error and all that things. So that's, I mean, I would say that the Druck control takes advantage of that deviation on the error in order to operate the system. So here you can see that here you have the reference, and the Druck control will control the voltage of the grid with a certain error. I mean, you are assuming a deviation of a plus minus 5% on the grid. I mean, you have to assume that. Then this deviation can be compensated by upper level controllers like secondary controllers and all that stuff that can change these references to make that this steady state voltage is just stable at the nominal values. But in any case, it is based on this principle. What it's doing, it's establishing a power sharing. So you have to imagine that if you have, for example, two nodes that are measuring the same voltage, okay, you have a power incoming from the wind farms, your voltage rises up, and then you have two different measurements, okay? You see, okay, my measurement is, for example, in per unit could be 1.05 per unit in both cases, okay? Based on that, you calculate the difference from the reference value, which is 1 per unit, so it's 0.05 per unit, and then you multiply that by a constant K that can be equal in both cases. Let's say 1, for example. Okay, so that is exactly what you are extracting to the grid, right? So this structure. You are extracting this current to the grid, right? So in both cases, if for example you include the same constant, what you will do is you will extract the same amount of power as in this case, okay? Then if for example somebody says, okay, but this is something that for example in some cases we can establish a power sharing that is not, you know, we probably in certain situations we want to send, I don't know, 50% of the power produced in the North Sea to the UK and 75% to Germany, okay? So we can do that because we can change the ratio between, for example, both constants here, okay? So it's not stacked, they don't have to be equal. For example, in an equal case, we are almost sharing the power between the two. So if we are injecting 400 megawatt and 400 megawatt here, we will extract 400 and 400 here, more or less. And if it's not like that because of the impedances, we will be able to compensate that. But for example, if we define this ratio here, so if we say that, for example, K1 is lower than K2, then we can scale that. We will see that later. But if we say that K1 is lower than K2, the grid side converter 1, as it is multiplying by a lower K, you know, it will extract for the same difference error on the voltage, it will extract less power, and the other one will extract a higher amount of power. That is what I wanted to depict here. So the power extracted on the one that has a larger value extracts more power than the other one. Okay. What happens, for example, related with the K value? If you have the same K values, then you assume that you will extract more or less the same amount of power. What happens if your K value, you can increase both or decrease both? What happens if, for example, you decrease both? Okay, so if you decrease both, you have a less aggressive controller, right? So you are, reacting smoothly to the error. So if you have a largest error, your control action, your power extracted will be, as you are multiplying it by a low value of K, it will smoothly go to the transient, right? That's what you can see here. There's not spikes here on the voltage. There's not huge oscillations on voltage, okay? But it is something that can take a while to get to the steady state, and the error, of course, as this K is lower, the error will be higher, but you have a less aggressive controller, right? So what happens, on the other hand, if we increase this K, it happens the other way around. You have a faster controller, you have an aggressive controller, you have your steady state error will be lower than compared to the other case, and you will see that we could at some point excite some resonances of the grid. You will see that the models that we are analyzing, I mean, if you model the multi-terminal grid, I will show you in 2 slides. You have to consider like parasitic reactances, inductances of the cables, because you know the core of the cable with the screen and all that stuff, they have like leakage inductors there, and they have some parasitic resistances to the earth. So it's quite complicated, and those combinations of resistors, reactances, and capacitors have some resonances that if we create an aggressive controller, we can excite those frequencies, and then we can see these oscillations that of course they are not desirable, because we can break, you know, if we have a huge oscillation on current, we can break the IGBTs, the converters, we can damage cables. If we have large peaks on the voltage, we can also, you know, exceed some protection limits and can trip the converters. So we have to stuck to the thing. Our idea when we started simulating these things, and we said, our question was, how can we design this case? And okay, because we want the power sharing, we didn't want it to exceed the voltage of the grid, because we want to maintain the grid voltage between 1 per unit and 1.05 per unit, let's say. And we don't want to trip the converters during the operation. We don't want to exceed 1 per unit in current or 1.1 per unit on the converters, right? Because otherwise we will burn them, or we will trip them as soon as they see a large current flowing through them, right? So that was our main goal, and we developed like a strategy, a control methodology strategy for designing these ideas to accomplish these 3 main goals: to inject the power produced from the wind farm with an established power sharing on the grid sites. Then we wanted not to exceed the DC voltage maximum ratings, and we didn't want it to exceed the maximum current on the converter. For that reason, the first step is to model the DC grid, and that's why we started doing working on this stuff. And all this stuff, that I'm going to present here is something that I did as a master thesis here in the UPC. So you could do, if you come here, you could do something similar related with HVDC. Okay, so here you can see, imagine a multi-terminal grid as I'm explaining. So it's N nodes, M nodes on the wind farm. So M wind farms. We wanted to do it generic. So we, thought about N possible interconnections and N onshore AC connections to the grid connected with R branches. Okay, it was completely generic code. Okay, so the input and output power nodes. This is the what we have. So we have the wind farm, and we were modeling them with just a simple current source. So they are essentially current sources. They are injecting some power, and we can know at some point if you have a wind farm, for example, of 400 megawatts, it won't exceed that 400 megawatts because it's maximum capability, of course. So we can model them like this. And regarding the grid side currents, we are modeling them on the DC side, not on the AC side, with a DC current source, of course. Okay, sorry. And we have the branch is to interconnect these branches. We are using something which is really, I'm not sure if you have seen the pi equivalent model for cables for power systems. So basically it's a pi equivalent model, right? So it's nothing weird, nothing completely strange. So if you keep in mind this structure, what we did is to basically include all this branch and input and output power nodes in all these things. So I spent half of my master thesis drawing this thing. So half a year or something like that. Yeah, it took a while to do that. So you can imagine that it was, I wanted to show that it was getting worse as soon as the complexity was, it was a bit of a nightmare, to be honest. So here you can see that you have the wind farm converters here, And basically what I'm showing to you is that you have non-controlled voltages, because you remember that you're not controlling the voltages on the wind farm. You are controlling the voltages on the grid side, okay? So these are the control voltages, the blue ones. Then you have the current coming through from the wind farms, which is something non-controlled. You know, you have a generation there, so there's something that is producing power, so you have an incoming of power there. And then this is the current that you can control. This is the voltage that you can control and the current that you can control, okay? And after spending 6 months on this thing, I finally thought that could be a good idea to work a bit with, the circuit equations, Kirchhoff voltage law, circuit laws and all that stuff, to obtain the the transfer functions of the system, relating my inputs, that were the grid side currents, the green ones, relating my non-controlled inputs, which were the currents coming from the wind farm, which were my perturbations, and considering my outputs, what way do I wanted to control? I wanted to control the DC voltages of the grid side converters, and we also have voltages of the non-controlled converters. So basically, I obtained a huge model, like a state space model of the whole multi-terminal grid, which you can configure if you change some stuff. Okay, and based on that, I decided, okay, let's analyze that, but considering as this thing, forget about all this stuff, and let's analyze that. Let's analyze this thing as if it were, just a control system, a simple control system. Okay. So for that, here you can see that there's not any drup installed. So I had to include like the drup control, and it is, as you have a drup control in each of the terminals, you have a multivariable drup controller, I would say, if you want to analyze the whole grid dynamics. So you end up, it is, as it is locally applicated, this is like a matrix, a controller matrix, which is just diagonal, because the drup 1 is just controlling the node 1, drup 2 just drup 2, okay, just node 2. And here you can see that it's quite simple. The first row is reference voltage, okay, minus the voltage at the point where it is measured, okay, so is this point here, multiplied by K1 is AM1, so it is the current that is flowing through this circuit. So as soon as we start seeing some voltage deviation here in EM1, it will apply some current and it will extract some current to the grid. And this was extended for the whole multi-terminal grid, right? So here, what I could do is if you see these blue and orange ones, so these are this blue thing here, which is the feedback for the drup control, which is multiplied by this K, which is this one. And then again, these are the grid dynamics of the grid. So as soon as I closed the loop, I was happy, because I spent 8 months then. So I had 3 months left to finish the whole stuff. And but then again, the question was already there. So I hadn't done anything. I have the model, but I didn't know how to analyze the whole stuff. I had just the model, the closed loop model of the system. Okay. So then I started with this 4-terminal stuff. Okay, so I said, okay, what do I have to do? I have 2 wind farms. Let's get stuck to a simple case: 4 terminals, 2 wind farms, 2 grid sides, then like a C interconnection between them. So it is, imagine if you have 2 different wind farms connected to the grid, and at some point you decide to link them through another cable. Okay. This is the idea. The nominal grid voltage I considered 150. It was done a long time ago, and for example 100 MVA. Okay, and my controller design specifications were, first of all, I want to inject the power, because at some point when you read some papers about this stuff, some people forget that your main goal is to inject the power that you're producing from the wind farms to the AC grid, and they start calculating some weird stuff like poles of the system, if it is stable or not, and they forget about the real stuff. This is the main goal here, okay? And then the second main goal is to establish the power sharing, okay? And because you want to maybe send some power different power. You have a set point of power that you must send to one country or another, for example. Okay, and then of course you have to do this safely. You don't want to exceed the maximum DC voltage, and you don't want to exceed the maximum converter current. That's something that the converter requires that to you, right? So I reduce the generic state space to this thing. So here again is a reduced version of that. Here you can see the 4-terminal stuff. So here basically is the reference voltages minus the grid side voltages, the control voltages, multiplied by the droop control. I am acting at these two different grid side converter currents. And then, well, basically here you can see the multivariable scheme that I was working on. Okay, so as soon as I had this thing, what I decided to use is to basically use multivariable feedback control techniques, because these, as you can see, these are all vectors, and the controller is multivariable because you have to control different voltages at the same time. So, well, that was interesting to see, and my feeling is that there's not in bachelor you don't see these techniques. You typically see PI, single input, single output techniques. So I had to study some multivariable feedback control techniques, but they are quite useful. So it's something interesting if you want to look at them at some point. So here are my conclusions were, okay, so if I want to extract, that we've seen that the power sharing was based on the ratio between one constant and the other. So if we want to establish an equal power sharing, it's simple. So we can design both constants to be exactly the same, okay? The problem is, how can which is the value of both constants? I can move them up or down, and then this will change the behavior, or this will change the maximum state, the maximum error, the maximum steady state error, the maximum dynamic error also, and also it will change the maximum current that will flow through my converter. So everything was a bit linked. So I decided to analyze two different, let's say, transfer functions. So one was related to the wind farm current. So as soon as a wind farm changes its current, what's going on? Okay, what's going on the error? So do I see some large peaks on the error? Do I see some smooth transient? What's happening? And then I wanted to see what's happening with as soon as you have some wind farm currents coming. What's happening with the grid side current also, right? So what's happening with the grid side current? I wanted to check that to avoid overcurrents on the converters. So based on that, I focused on these two different transfer functions, and what I did is I applied like a similar. It is like a Bode diagram, but for multivariable systems. So you can imagine that a Bode diagram gives you the gain of the system. So if you have multivariable systems, you will have directions on, it is a vector, so there's directions of inputs, directions of outputs, and there's depending on the direction of the currents at the input and at the, for example, if you excite the system with 400 and 400, is not exactly the same as exciting the system with 400 and 0, okay? It's not exactly the same condition. So basically, analyzing with what it's called singular values, it's like it gives you the maximum gain of the system for any possible input. So it says, okay, my system is going to amplify the input that much, considering the worst possible case, okay? And if you know the worst possible case, and if you know the worst possible input, you can limit the behavior of your converter. So what we knew here, we knew that our possible case on the wind farm currents it's what it is that if we have a step input at both, it is impossible, of course, but if we have from 0 to 400 megawatts at some point, for example, let's say at a certain instant, you imagine that you have a perfect wind farm and it can increase the power step. So imagine that you can establish a 400 megawatt step at both sides at the same time. So that's the worst possible case scenario, and that's what we chose for that. And then we decided that the maximum possible, the the worst error that we wanted to have in the system was 1.05 per unit, so a maximum deviation of a 5%. Okay, so if we know this maximum input, and if we know the maximum output that we want to allow on our system, we can limit the gains of the system. We can limit this gain. Okay, so based on those values, I calculated these limitations here. Okay, and these are the gain of this transfer function. So all the system gains that are far away, that are above this shadowed area, were not suitable for the system because they were exceeding the system error defined by myself. Okay, and here you can see something interesting. For example, there are a steady state case. This is zero frequency, right? The steady state case is quite simple to analyze. You don't have to use dynamics for that. But here you can see that these peaks, at some point, they could exceed this shadowed area, right? So we wanted to check if those peaks were not exceeding. This is the dynamic behavior. This is what causes that, for example, in case of a step input from both wind power plants, you will have a voltage that goes above just for a short frequency, and it will be a large frequency peak, a high frequency peak, but it can exceed the maximum voltage, and it can trip some converters, or it can lead to not unstable operation, but it can trip something, or it can create some failure somewhere. Okay, so that's what we see, and here you can see that values higher than 1/22.5, which is this limit here, we said that they were suitable for the system. Okay, then the other let's say transfer function that we analyzed is that, as I said before, the current relating the wind farms and relating the current from the wind farms to the current from the grid side. So if we have a 1 per unit input on the wind farms, we don't want to exceed the 1 per unit output on the output, because otherwise we will burn the converter. Okay, we have a margin for that because the converters always have a bit margin, or they are underrated, but there's not something that you can exceed the converter rating 2 times, as for example in synchronous machines or the stuff like that. Okay, so that's what we defined, and well, basically is exactly the same procedure as before. So the things below the shadowed area were suitable for the system, and these high peaks, these large frequency gain peaks, is what you could see in some systems, that you could see something that does this kind of rippling. So if we, for example, select this one, which is a large droop, you will see what the things that I've shown you before, that it's something that is doing this kind of ripple thing. So as soon as the converter goes up above 1.05 per unit in current, it will trip. So we cannot program this 1 per unit, so this droop equal to 1, so we have to go to a lower value. So between those two, once, let's say, the error defines a minimum value, the error defines a maximum value of droop, and the current defines a minimum value of droop. So between those two, we can, no, on the other hand, so the current defines the maximum and the error defines the minimum. So in that way we can operate the converter in that area. Okay, so based on that, I selected 2 different constants on that range, 2 at the same. I selected them to the same value, and I did some simulations. As I said, some worst case scenario simulations. So I tested 2 different power step inputs of 100 megawatts from both wind farms, which is these square wave steps. And here you can see that, for example, regarding the power, here you can see that the power is quite smooth. It has some oscillation, but this is because we are exciting it with normally this is evolving in terms of 100 milliseconds at most. So, and even less, because the turbines has some filters like the blades and all that stuff, so they are a bit more smooth than compared to this. Okay, but even in the worst case scenario, they were behaving pretty good. For example, regarding voltages, here you can see that this is the reference voltage, and as soon as you have this power input, as you have the proportional controller, it stays under the, I think that we define for this case a maximum deviation of a 10%. So here you can see that it is evolving to the steady state, but it's less than a 10%, right? And well, basically, and here something interesting that you can see is that all nodes, E1, E2, E3, E4, all the voltage nodes are, more or less at the same level. So here you can see that the loss, that the voltage drop between one and the other are not that much. So we are kind of, all the voltages of the multi-terminal grid are more or less at the same level, okay? And then in terms of current, here you can see that this I3 and I4, which are the currents of the MMC on the grid side, are not exceeding this, the maximum current, because they have a smooth transients, which is the design that we have proposed. So, well, based on that, it's basically